Stopped recording. Okay. Part 2. We are converting the volume 15.3 meters cubed into decimeters cubed. You first start off by doing it linear, right? You always start with a linear conversion and then raise it to the appropriate power. If it's an area conversion, you raise it to the power of 2. If it's a volume conversion, you raise it to the power of 3. We're going to practice this because I want you guys to get good at this. If you get good at this, then a lot of what we do in science is going to be a lot easier for you. So I've raised this to the power of 3 because it's a volume conversion. 10. So when I distribute that power of 3 in there, I'm going to get 15.3 meters cubed times 10 cubed is 10 to the power of 3. You could just write that like that. Decimeters cubed, 1 cubed is still 1, and then meters becomes cubed. Now you've distributed the 3, so you don't write it again. You can cancel the meters cubed, and what you get as an answer is 15.3 divided by 1 doesn't affect anything, so you've taken that into account. 15.3 times 10 to the power of 3 decimeters cubed, and then you just convert it to the proper scientific notation by moving the decimal over by 1. You get 1.53 times 10 to the 4 decimeters cubed. That's your final answer. If we want to go to kilometers, 15.3 meters cubed times conversion factor for linear meters to kilometers. How many meters are in a kilometer? Kilo. What does that mean, kilo? It means 1,000. Right? When they dropped the bomb on Hiroshima, it was supposedly a 0.1 kiloton equivalent. When they talk about atomic bombs, they compare them to the amount of dynamite that they're equivalent to. So a 1 kiloton bomb gives you the same size of explosion as 1,000 tons of dynamite. They did a test. They calibrated it in the 1940s. They literally took 1,000 tons of dynamite, made it into a cube, and they detonated it, and they made a little mushroom cloud, and they measured the height of the mushroom cloud, and from that they were able to assess the power, the destructive power of an explosion. So the bomb they dropped on Hiroshima was approximately 0.1 kiloton. It was like blowing up 100 tons of TNT. The biggest bomb they've ever exploded was the Tsar bomb in Russia. It was a hydrogen bomb, and it was a 57 megaton equivalent. So it was the equivalent of exploding 57 million tons of TNT at once. It made a cloud that was something like 40 kilometers wide and went way up into the atmosphere. It was the biggest bomb. Yeah, the mushroom cloud just kept on going up and up and up, and it spread out to something like 40 kilometers across. So it was huge. If they were to explode such a bomb, say in Toronto, I'm pretty sure the devastation would annihilate downtown, and you would have damage extending all the way to Oshawa. And then, of course, the fallout would be another issue you have to deal with, because atomic bombs they hit you 3 times. They get you with the flash of light, then there's the shock wave, which goes in 2 directions. You get a shock wave going out, and then you get a shock wave coming back from the air that's been displaced. And then finally you get the fallout, all the radioactive particles that come raining down and poison you with the radioactivity. So if you don't get hit by if you don't get cooked by initial flash, you get blown away by the explosion in both directions and flying debris. And finally, if that doesn't kill you, the radiation will poison you. So it's a horrible weapon, and it should never be used. And any country that was stupid enough to use one would then be retaliated upon by whatever country they had used it upon. So they call that mutually assured destruction. And the best way to deal with such things is to never make them, and to learn diplomacy. The next thing is meters then. So 1,000 kilometer is 1,000 meters. So 1 kilometer per 1,000 meters. Why did I put meters on the bottom? Why didn't I just put meters on top and kilometers on the bottom? There's got to be a reason. Any ideas? what am I trying to eliminate? I'm trying to get rid of meters, so I gotta put meters on the bottom. I'm gonna put this over here so it's more straight. Just let this angle going on. Then I'll be standing in front of it. Okay, we'll see. Power of 3 then. And raise this to the power of 3. So that's equal to 15.3 meters cubed times 1 cubed is still 1. Kilometers cubed becomes km to the power of 3. What's another way of saying 1,000? 10 to the power of 3. What happens when I raise 10 to the power of 3 to the power of 3? No? Multiply them. Good. You get 10 to the power of 9. All right? And then the meters becomes to the power of 3. There's your bracket with the cube distributed into it. Now we can cancel out meters cubed because they're the same there. What's another way of writing this 10 to the power of 9 in the denominator? What if I bring it upstairs? Good. So you get 15.3 times 10 to the power of 9 kilometers cubed. And to put it in scientific notation, I put this over to there, so it's 1.53. I've made this 10 times smaller, so I'm going to make this 10 times bigger, so I'm going to raise its power to negative 8. Remember, when you raise the power, you're making it less negative, so that's why you go up to 8. So you get kilometers cubed. So 15.3 meters cubed is equal to 1.53 times 10 to the minus 8 kilometers cubed. And now let's go to conversions to centimeters. Do you think you can do it by yourself yet? No. Okay, pay attention so that it makes sense to you. 15.3 meters cubed. I appreciate your honesty, though. Tell me if you don't get it. Don't pretend you get it if you don't, because then I'm going to assume you do, and we'll move on, and you won't get it in the next step. So I'll spend as much time as you need to get this, but concentrate, pay attention. Let's try to see what I'm doing. Centimeters. What's the linear conversion of meters to centimeters? How many centimeters are in a meter? Centi. Okay, we went over this before. So 100 centimeters per 1 meter. Again, I put meters on the bottom because I want to get rid of meters. So I want to be able to cross it out eventually. That's going to look like that. I'm going to rewrite it now so that we distribute the cubed into the bracket. What's another way of saying 100? 10 to the power of 2. But it's raised to the power of 3, so it becomes what? 10 to the power of 6. And it's centimeters cubed. The 1 still is 1 because 1 times 1 times 1 is still 1. And the meters becomes cubed. Meters then can cancel. And you have 15.3 times 10 to the power of 6 centimeters cubed. Put this in scientific notation by moving the decimal over by 1. You have 1.53 times 10 to the power of 7 centimeters cubed for converting, if you want to convert it from 15.3 meters cubed. Last one now, we're going to convert into millimeters cubed. 15.3. You notice how much use I've made of a calculator. I haven't touched the calculator because all these are factors of 10. You don't need to use a calculator if you know how to work with exponents. If you know your times tables, it also helps, right? A lot of people don't know their times tables. I don't know what you did in elementary school. Too many crosswords, not enough math. Okay, so that stuff should be learned in high school. By the end of grade 6, times tables should be not an issue at all. But there's some crazy educational theories floating around where they say it's not good to memorize stuff. I reject that notion completely. You have to memorize many things if you want to be competent. The notion that memorization is bad is a completely false one. You memorize many things. You memorized how to open a doorknob. You never think about it, right? You just do it. It just happens. Why? Because the pattern's already in your brain. You memorized how to ride a bike. You memorized how you put your pants on. Imagine if you had to think about everything. Imagine if you had to think about breathing. Fortunately, a part of your brain takes care of that. So there's nothing wrong with memorizing things until they become automatic. And you'll notice that whenever you're learning a new skill, the only way you can get good at it is when you do certain parts automatically. Like if you play guitar, anyone here play guitar? Or any other instrument? you know where the notes are, but when you're first playing those notes, you see how they are on the paper. You're doing them one at a time, and it's terrible. After a while, your fingers just do what they're supposed to do, but you're not thinking about where the notes are. You're just doing it with your hand motion because you've memorized through your kinesthetic sense how it's supposed to feel. And then you can start thinking about phrasing, how you're going to bend the note or waver it a little bit to make it sound more, evoke whatever emotion it is you want to evoke with the piece. So as you memorize certain parts of what you're doing, you can spend more time thinking about the other parts of it, which are the finessing of it, okay? We're going to millimeters now. So there's 1,000 millimeters in a meter. And you're raising it to the power of 3, right? Because it's a volume change. Another way of rewriting this is 15.3 meters cubed times. What's another way of saying 1,000? What's another way of saying 1,000? 10 to the power of 3, but you're raising it to the power of 3, so it becomes what?
6.
No? 9. 10 to the power of 9. Remember the rule of exponents. When you raise a power to a power, multiply. When you're multiplying exponents, then you add the exponents. When you're multiplying things that are raised to a power. So 10 to the 9 millimeters cubed per 1. 1 is still cube. 1 cubed is still 1. And then meters cubed. Meters will cancel. And you have an answer, 15.3 times 10 to the 9 millimeters cubed. And you can rewrite it in scientific notation by moving that decimal over. You get 1.53 times 10 to the power of 10 millimeters cubed. So 15.3 meters cubed is equal to 15,300,000,000 millimeters cubed. And that covers what I want to do for unit conversions. I think you should be, you have enough material there to learn what it is that you need to know how to do. And I will be giving you questions. Your first test is going to be based on doing this stuff. I'm hoping that you picked it up. Watch it again when you're at home, if you don't understand it, and then try to do it on your own. That's the best way to prove to yourself that you've understood how to do it, is you do it without any coaching. The next thing I want to look at is density calculations. Let me show you a typical density calculation. It's on page 20 of the textbook. It says, calculate the density of a 374.5 gram sample of copper if it has a volume of 41.8 centimeters cubed, okay? So whenever you do those types of calculations, they're usually 3 variables. They're gonna give you 2 of them. You gotta figure out the 3rd one. So I use a little bit of simple algebra to isolate the variables. Let's show you how that works. Density, by the way, is a measure of mass per volume. What's denser, water or wood? A bit of a trick question. What's denser, water or wood? You might be tempted to say wood because wood is a solid and water is a liquid. But density is a measurement of mass per unit volume, not the consistency of the material. But water is denser than most woods because wood floats. If something is denser than something else, it won't float in it. If you put a piece of iron in water, the iron sinks because the iron is much denser than water. But if you put a piece of iron in a dish of mercury, the iron will float because mercury is denser than iron. Mercury has a density of 13.9. Iron has a density of 7.85. So iron will definitely float in water. How is it possible for iron ships to float in water? How does a battleship float when it has walls that are a foot thick made of steel for armoring? How is it possible that they're floating on water? It's called buoyancy. The ship has large empty spaces inside, so its average density is much smaller than the density of the material that it's made of. A ship displaces exactly as much water as it weighs. So if a ship weighs 50 tons. When you put it in the water, the ship is gonna push 50 tons of water out of the way, and then it'll float. But if the ship weighs more than the water that it displaces, then it sinks. You ever notice when you go swimming, if you take a breath, you float. When you let the air out of your lungs, you sink. Why is that? Because your density is very close to the density of water. When you take a deep breath, you fill your lungs with air, you bring down your average density, so it becomes less than the density of water. If, on the other hand, you blow the air out of your lungs, your average density is greater than the density of water, so you sink. Even if you hold your breath, when you go deeper in the water, the pressure of the water pushes your chest down, so you actually, at some point, you become denser than the water, and you start sinking without even trying. And makes it easy to go, if you go snorkeling, that's one of the tricks that snorkelers use when they go. I spent the summer, I was 15 in Italy, and I used to go to the beach a lot. And one of the things that we could do on the beach was we would dive for sea urchins. So you'd wear your mask and a snorkel, you'd go down like 20, 30 feet in some places, and you could get these little sea urchins. They have all these black needles sticking out, but when you open them, you can turn them upside down, you can cut them, and it's like an oyster inside. It's really tasty. And I had a great uncle, a second uncle, he would go down like 30, 40 feet and get these bunch of sea urchins. He could hold his breath for a long time. And anyway, it was a good pastime. You get pretty good at holding your breath if you practice. Some people go for several minutes underwater holding their breath as if they practice enough. So anyway, this is page 20 of the textbook practice example. We're using the formula density equals mass over volume. So density is represented by the Greek letter rho. Okay? And its units are typically grams per centimeter cubed. The mass is in grams. Mass in grams. And finally, volume in centimeters cubed, usually. So the volume, the density of water happens to be pretty close to 1. Water is at its densest. Here's a cool fact. Water reaches its maximum density when its temperature is 4 degrees Celsius. So if you go to the bottom of almost any lake that's deep enough, guess what the temperature at the bottom of the lake is? 4 degrees Celsius, yeah, because that's where the densest water ends up. Because water likes to stratify according to density. If you go scuba diving, you can actually see that. The deeper you go, you see these layers where there's actually like a line. And when you cross into the lower layer, it's colder, usually a lot colder. They're called thermoclines. So if you're not wearing a wetsuit, you literally bounce off it because it's so cold. You don't want to go into that water because it's super cold. But if you're wearing a wetsuit, you can take it, especially if it's a full body wetsuit. If it's a short wetsuit, then not so much because your legs get cold. Let's do the numbers on this. So density equals mass over volume. We're told that the thing weighs 374.5 grams. And its volume is 41.8 centimeters cubed. So the density turns out to be 8.959, 33014 grams per centimeter cubed. And we're gonna round it down to 3 sig figs because there's only 3 numbers in this and 4 numbers in that. So the most accurate number we can use only is gonna have 3 numbers in it. So we're gonna say 8.96 grams per centimeter cubed as our final answer. That's called using significant figures because it makes no sense to write an answer with 10 numbers in it when the numbers that you used to calculate it only had 3 numbers in it. Part B, it asks, a student needs 15 grams of ethanol for an experiment. If the density of ethanol is 0.789 grams per milliliter, how many milliliters of ethanol are needed? Now it's asking you what volume you need. So in B, it says density equals mass over volume. We're going to be looking for the volume. So let's try to isolate volume. How do we get volume, the letter V by itself? We're going to use algebra. Multiply both sides by V. That cancels the V on this side and it puts it over there. But now it's next to density, so I want to get rid of density. So I'm going to write my modified expression, and I'm gonna isolate V by dividing both sides by rho. So divide both sides by rho allows me to cancel rho over there, and what do I get? V is equal to mass over density. So I've isolated the volume. Now I can plug in my numbers. The two things I am given are the mass and the density, and what it is 15.0 grams over 0.789 grams per milliliter. And so you need a sample size of 19.0114068 milliliters, which rounds to 19. You're only allowed 3 sig figs in the answer, so 19.0 milliliters of ethanol. Last one is part C. You're still seeing all this, yeah. Can I erase? Or is it too early? The densest metal in the universe is, well, I don't have a periodic table. Anyway, the densest metal in the universe is osmium. No, sorry, iridium. Both osmium and iridium are very close. But iridium has a density of 22. So it's about almost 3 times the density of iron. So if you had a block of iron this big, it would weigh about 9 pounds. A block of iridium the same size would weigh about 27 pounds. So it's a very dense metal. And in fact, scientists use the presence of iridium in the crust of the Earth as evidence of an asteroid strike. And the thinking behind it is pretty simple. Because iridium is the densest metal, where do you think it usually ends up in a planet? It usually ends up in the core. Because when a planet first forms, it's very hot, and so all the heavier metals tend to sink lower into the planet. So you get the highest concentrations of nickel, iron, and all the metals in the center of the planet. So sometimes when a planet breaks up, that's how you get asteroids. If you go between the orbit of Mars and Jupiter, there's a whole bunch of large rocks, some of them, hundreds of miles across, that are the result of some kind of planet that got broken up because it got too close to Jupiter. Jupiter's gravitation is so strong that it can literally break apart a planet if it gets too close. So that must have happened at some point in the primordial solar system, and it made an asteroid belt. Once in a while, these asteroids bump into each other, and one of them starts flying in the direction of the sun. And in the early solar system, a lot of these rocks were flying around, and a lot of them hit the Earth and the Moon. Fortunately, it happened in the early solar system, so now the solar system is pretty clean, comparatively speaking, although there are still things flying around. But when a large asteroid hits the Earth, if it happened to come from closer to the core of an old planet, it's going to have a high concentration of iridium, which is why scientists believe that the Earth, all the dinosaurs were wiped out by an asteroid 66 million years ago. Because if you go all over the planet Earth and you dig down to the layer of ground that's 65 million years old, because the deeper you dig down, the older the layers of dirt are. If you go to the layer of dirt that's 65 million years old, all over the planet, there's a thin layer of iridium dust. So sometime 66 million years ago, something really big hit the Earth. It made a huge dust cloud that circled the whole Earth, and then it settled back down on the Earth, and that iridium is slightly radioactive, so that's how they can tell. And scientists believe that the Earth was hit by a giant asteroid back then, and that dust cloud it raised, they theorize, is what made the dinosaurs die off and deposited that layer of iridium. We've also had a big asteroid hit 1 billion years ago here in Sudbury, actually that way. North is that way. A giant asteroid hit the area close to Sudbury, and it was a big asteroid full of nickel. Guess what kind of mine they have at Sudbury? A nickel mine, yeah. They go dig underground. Guess what they find? Pieces of the asteroid. So the ground is very rich in the area around Sudbury. If you drive close to Sudbury, you can actually see areas of the ground where it looks like lava was flowing. And it's from 1 billion years ago, because when the asteroid hit, it just melted rock and it just shot ejecta everywhere, and it made a mess. There's even areas where the rocks are broken in a certain way. They're called shatter cones. So the breaks in the rock means something hit the ground so hard that the vibrations made the rocks crack. And there's evidence of it all around Sudbury.
Do you think
Do I think what?
One of the
The
rocks.
pieces? Oh yeah, there are pieces everywhere. If you looked around and if you know what you were looking for, you'd probably find pieces of nickel-rich rock. But mind you, it happened 1 billion years ago. So little rocks would have gotten washed away.
Yeah,
But really big ones would have been
but
would still
since
be.
you're saying the rocks hit each other, you think one is gonna hit directly to the earth?
Sure, yeah, eventually something will hit us, yeah. But I wouldn't worry about it. You have a better chance of getting struck by lightning or eaten by a shark or kicked by a donkey. You know, when you look at the statistics of what kills people, people worry a lot about stuff that they shouldn't worry about. You know, if you have a swimming pool, here's a statistic that should blow your mind. If you have a swimming pool, you have a 200 times higher chance of somebody dying at your house than if you have a gun. There's a guy I know, he lost his daughter. He found her in a swimming pool one day. He came home, she was drowned. She drowned in a swimming pool, 16-year-old daughter. She slipped and fell, I don't know what happened, but she died. I don't know of anyone who died because of a gun, personally. Although, when I used to live around here on John Garland, there was a shooting every 4 months. I never knew any of the people, but there were shootings. So, yeah, statistically, if you look at the stats, people die for silly things. You know what people die a lot of from? They die of car accidents. They die of falling down the stairs, slipping and falling in their tub. You know, they even did a calculation once where suppose we were suppose we were immortal, that we didn't die of disease, we would still die. But the calculation, according to actuarial mathematicians, is that on the average you would live about 1,100 years if you were immortal, but you would die by misadventure. One day you would fall off a ladder, or you'd slip down the stairs, or you'd get into a car accident. You would still die. It would just be because of an accident. But normally our lifespan is 87 years, something like that. So people usually die after a normal life. But if you live long enough, you will have an accident that will kill you. You die by misadventure. So even if you're immortal, if a big rock falls in, you die anyway, right? That's the idea. There's even I forget where I read it. It was about it was a philosopher who's, I don't know if it's a true story, but the story goes that somebody prophesied to a certain person that he would die from a house falling on his head. So the man spent his whole life worrying about a house falling on his head, so he used to stay outside all the time. And then one day, an eagle was trying to eat a turtle, and he dropped the turtle from a high altitude to kill it, and the turtle landed on the man's head and killed him. So it's kind of like a fatalistic story. Like, don't worry about things that you have no control over, because it happens. It's going to happen when it happens, right? The last one. See. Don't start packing. I'm still teaching. 10 more minutes, guys. Just hang in there. I'm almost done. In the part C, let me read you the question. It says, what is the mass in grams of 25 milliliters of mercury with a density of 13.6? So in this case, they give you the volume and they give you the density of the mercury, so they want the mass. So we're going to rearrange the equation so that mass is by itself. And then we'll plug in the number. The density of mercury is 13.6 grams per centimeter cubed, or millimeter, because millimeters and centimeters cubed are actually the same thing. And it's got 25.0 centimeters cubed. So you have 340 grams of mercury. Just remember this, 1 centimeter cubed equals 1 ml. It also equals 1 cc. Sometimes you see this, it's not an SI unit, but it means centimeters cubed. It's the same as that. Okay. Conversions, notes. What we've been doing is called we haven't really done dimensional analysis too much, because I haven't really shown you how to convert units so much. I've just shown you how to do some simple formulas. I think that over the next 15 minutes, I'd like to show you how to do dimensional analysis. We'll see how far we get into it. Dimensional analysis. So to convert from one measurement to another, I must say, I kind of like the atmosphere in the school right now. You don't hear anybody screeching in the hallways. But I'm getting the feeling that distance education doesn't cut it. It's not as good.
There's two more cases positive.
People are people getting sick or testing positive? Okay, the testing positive?
Yeah,
Yeah, but whatever.
there were teachers. It was teachers told them.
Yeah, but testing positive, what does that mean? It means you got a sniffle? Do you get
No,
aches?
they're positive. I don't know. They're positive and
I'm not buying it.
there was a big drama.
Yeah, big drama is right, yeah. Like acting. Imagine a pandemic that has no symptoms. Laughable. This is not to say that the virus is not real. It's real. It does kill people, but I think it's over. You know why Italy had a big outbreak? It was all concentrated in northern Italy around Milan. Milan, what is Milan the capital of? What is Milan famous for? It's the capital of high fashion. That's where they have all those models, you know, strutting on their, you know, they have all these fashion things. You get guys like Gianni Versace and all their new designs for the spring, and they sell all their stuff to the people. Anyway, Milan is where they have a very active textile industry. Guess who they trade with for textiles? Guess where they buy all their cheap textiles? China. Wuhan, to be precise. So that's where there was a lot of travel between those two countries. That's why there was an outbreak, because the thing started in Wuhan. So let's do an easy conversion here. How many eggs are in 3 dozen? Everybody knows this. Okay, how many eggs in 3 dozen? 36. How did you know that? Uh-huh. Right. You get 36. All right, so you knew the conversion factor. You used the conversion factor without even being taught conversion factors. So you already know it a little bit. Here's how it looks. So a dozen can be expressed as 12 eggs per 1 dozen, or you could say 1 dozen for 12 eggs. You ever have any chickens around you? My dad has chickens at his farm. They follow you around. If you give them food, they start following you around. When they see you, as soon as you come outside, they all run towards you.
Yeah, because they think every time you come out.
Yeah, there you have food. And so, how did I get 36? Well, I had 3 dozen. And it's funny because they'll spend all day outside. They'll just walk around all over the place. Then when the sun starts to go down, they all come back to the coop by themselves. They just all walk back and they sit down and they sort of tuck their head on their body and they fall asleep. And they like to dig a little hole so they feel comfortable. And they sit in a little hole in the ground. And if you know what's funny, I watched, if you make a rooster sound, all the hens stop for about 10 seconds. So if you go, they all go like this, and they stop moving. It's a funny instinct they have. roosters are really annoying though, because they never stop making that sound when the sun is up. There, you see how I canceled dozen? You can cancel whole words, you can cancel numbers, you can cancel letters. I'm canceling dozens, and I'm multiplying the numbers. 3 times 12, 36. How much? Eggs. 36 eggs. Okay? And I wrote here, notice how in one of the terms, dozen appears in the numerator. Right here. This is in the numerator. I didn't write a denominator because there's no need. It's over 1. But if it helps you, write a 1 under there to show you that this is a numerator. Now, and in the other, it appears in the denominator. Why did I put it in the denominator? See, I had 2 possibilities. I could have put dozen on the bottom, or I put dozen on the top. Where does it help me? It helps me when I put it on the bottom. It's saying the same thing. 12 eggs to the dozen, or 1 dozen to the 12 eggs. You're saying the same thing. But you're going to use the conversion factor according to need. So I used the one where dozen is on the bottom because I want to cancel dozens. And that's how I get the correct answer. If I use the other one, I'll get a wrong answer. So you got to know which thing you're canceling. And that is the main idea of dimensional analysis. I guess I'm losing the battle with you today. Everybody's on their phone. I've lost. I'm jealous. I'm jealous of the phones. I should come and dress like a phone. Maybe you'll look at me. What do you think? If I wear a cell phone, then you'll watch me. Okay, let's do a couple more examples, then that's it, because they're gonna, actually, you know what? Let's stop it right there, because nothing's going in your minds right now. You're done. So we'll continue this next class. But feel free to look up conversion factors on my profile, and I will post this tonight.